we're back. We're live. We're at ThinkTech Talks. We're the SOEST Hour, the School of Ocean and Earth Science and Technology in UH Manoa. Wow, exciting. And our show today is Petrological Puzzles at SOEST. Did I get it right? Okay. Also known as Unlocking the Mysteries of the Deep.
Using rocks.
Of the super deep. Unlocking the rocks of the deep. Okay, with our special guest, Julia Hammer. She's a volcanologist, a professor of geology at UH Manoa in SOEST, and Emily First, a graduate student at SOEST. What are you studying, Emily?
Well, I'm studying igneous petrology, technically, which is basically the study of igneous rocks, so rocks that come from deep, hot processes in the earth.
Okay.
And I do a lot of lab work with Julia, kind of making my own rocks, if you will. But I also take a lot of classes in different geological processes, like volcanology.
Our job today is to show them that what you do is dramatic, romantic, exciting, and you are in touch with the mysteries of the deep. Okay? And maybe
Right.
they will sign up too. They will sign up and come, and work with you in the laboratory. That's what.
All right.
Okay, Professor Julia Hammer, let's start with you. What role do you play in SOEST? What role does your work and your department play, volcanology play, in the panoply of SOEST at UH Manoa?
Okay, well, I'm in the Department of Geology and Geophysics, which is an academic unit within SOEST. So we teach classes, we teach undergraduates, and we have a very vibrant graduate program. So a lot of what I do is instruct, and I teach at the introductory level and at the kind of majors level. I teach a mineralogy course, and then I also teach at the graduate level. So I spend a lot of time preparing classes and instructing about rocks, basically, and minerals and geology. And the other side of life is the research component.
Before we go,
Okay,
teaching.
yes.
Okay, are your students in SOEST, are they from SOEST, or is it a discipline that, that other students from other parts of the university can, should, or are required to take as part of, their curriculum?
Well, at the undergraduate level, the introductory courses satisfy science distribution requirements and laboratory distribution requirements. So we get majors from all over campus: education, business, everything. And that we take that very seriously, because for a lot of those students, it might be the last science class that they take, the last formal exposure to earth science. And so we are compelled to do as good a job as we can of transmitting why it's important as citizens of the earth to understand the planet we live on.
Citizens of the earth. There's another title for the show: being good citizens of the earth.
Right.
That's what SOEST is all about. Earth is its middle name, so to speak.
That's right. And then at the mineralogy level, that's a 300 level course. So by that point, we really only have the people who have chosen geology and geological sciences as a major for the most part.
So they would likely be students in SOEST, so to speak.
Right, that's right. And some of them come from other units within SOEST, like oceanography. Sometimes some of those students take that class. But it's required for the Bachelor's of Arts and the Bachelor of Science in the Department of Geology and Geophysics.
But somehow SOEST plays a kind of central role in the university, because, I think Hawaii is and must be really conscious of its surroundings, of its earth and its ocean. And that's where that study lives, in SOEST, yeah?
Yeah.
So it's, to me, I see the campus as kind of, I know it doesn't work really this way, but I see the campus as kind of all around SOEST. I see SOEST in the center, the conceptual center, because the land and the ocean and all that is in the conceptual center.
Yeah,
of the
I
islands.
think geology and your local environment, that the earth that you're standing on, is central to identity.
Yeah.
As a person, you are kind of defined by.
Yeah, and we as a
Your
group, as
relationship
a state, are defined by it. And when we forget that, we're in trouble. We have to remember that, because it's all we got, so to speak.
Yeah.
So how did you get into this? Where did you start? When did you have let's start with Emily. When did you have the revelation this is what you wanted to do? Were you in the shower or what?
I wouldn't really call it a revelation. I've actually really loved rocks and volcanoes specifically since I was a kid. I mean, when I was really little, like kindergarten, I would watch the National Geographic volcano specials. And,
Okay.
but then it's unfortunate we don't really study it much in like the high school level in schools, so it sort of faded from my mind a little bit. And then I started taking undergraduate classes at the University of Georgia, where I got my degree. And I really enjoyed the interlevel geology, did a field program across the country, and saw Mount St. Helens and some other volcanic fields. And that kind of really cemented, like, yeah, this is what I want to do. And then to the point that I decided to do grad school. Came here and visited, and seemed like a really good fit. And now I'm in my 3rd year.
Can you identify what it was, about rock and geology that turned you on?
I mean, on a very basic level at first, I think it's because I thought volcanoes were so beautiful.
Yeah.
And then also, I guess, sort of the juxtaposition of having something so beautiful that's also so dangerous and can affect people's lives so much.
Yeah.
Kind of the active
There's
process.
your drama.
Yeah.
Yeah,
There's the
I'm looking
romance
for
and
drama.
drama.
We found it
Romance
already.
and the drama.
We're in the show 5 minutes and we found the drama.
Yeah. So that was originally it. And then, I don't know, just sort of being able to look at that rock kind of like a puzzle that tells you about what happened before it, and that could even tell you more about the planet depending on what you're studying. It's just like a giant puzzle, which I love.
Part of that, seems to me, part of that is a timeline. Because if you understand geology, am I right? Tell me if I'm wrong.
Yes.
If you understand geology, you can sort of, and there's almost the beginning, Genesis kind of thing, till now. And geology gives us a kind of window into that somehow.
Yeah,
In terms of finding the age of this or that.
Yeah.
They talk about it as the 4th dimensional science. So we have 3 spatial dimensions, and then without time, there's no geology. So
Yeah. Without time, there's no geology.
Well, maybe.
That's great. No, that's a great concept. Okay, and what about you, Julia? What was your epiphany?
Well, I did have a National Geographic moment when I was in high school, and I saw a photograph of a scientist from actually, now he works at the Hawaii Volcano Observatory, but he was running away from a Kilauea eruption, but not just like running for his life, he was cradling rocks in his arms while running for his life. And I was thinking, that is incredible. What a job that must be, to care about the science so much that you will, do what it takes to get the samples that can unlock the secrets of the volcano. But I don't actually practice it at that level these days.
But
I have kids.
But
But
you don't run around with rocks like that.
Yeah, that was a moment. But just like Emily, we don't study it or science so much in high school. So it wasn't till college. I took a few classes in the Department of Earth Sciences at my college, and it was at that point it became a story of the people, the personal relationships that majors in geology have with their instructors are so close and deep compared with other majors, because it's usually a very intimate group, and you go on field trips together, and so you're spending nights in a tent with your colleagues, and you kind of develop a rapport that's not possible just classroom learning. So I think, like a lot of people, I got drawn in by the field aspects of it, and being able to travel as part of your work.
Have to, yeah.
Yeah, and wherever you go on the earth, there is something interesting to see and do just by nature of the geology that's around you.
Yeah.
So
I don't know why, but I remember the old line about real estate. Real
location.
That's the other one. Real estate is not about land, it's about relationships. And you could say the same thing for a lot of things, but it includes, geology. Geology is not about rocks, it's about relationships.
Well, it does turn out that way. I mean, the care and feeding of the undergraduates is typically pretty good in a geology department. The scientists are, by and large, very friendly people, down to earth, as it were.
Oh,
and
Down to Earth is another title. We were having trouble finding a title for this. Now they're coming out of the woodwork. Down to Earth with geology. Sorry, I interrupted.
That's okay. No, so there was that combination. Plus, if it hadn't been geology for me, it would have probably been chemistry. And so that has influenced the direction that I've taken within my research, as I'm on the chemistry side of volcanology.
You'll have to explain that to them. Why is chemistry so critical in geology?
Oh.
They're waiting.
Chemistry is critical in geology because it describes how atoms interact, and we're just talking about atoms of natural materials, be they silicate melt or crystals or vapor phase gas bubbles that drive volcanic eruptions. At every level there are chemical reactions and interactions, so it's quite possible to focus on chemical aspects, but it's even more powerful when you can marry it with physical. So the intersection of chemistry and physics is really an exciting place in volcanology.
Oh,
that's the frontier.
Really, we're starting to really get lined up over here, and to understand. So what about, I think we'll take a short break, and we'll come back. And when we come back, I'd like to ask you, what about these volcanoes? Because you guys study volcanoes, and it's really an important part of geology, I think. It's sort of our view into the center of the Earth. That's another good title, View into the Center. And you'll tell us about what it is, volcanology, what you have to learn and do, and how it works from a research point of view.
Okay.
We'll be right back. This is Jay Fidel. We have Julia Hammer and Emily First, both with SOEST. Julia is a professor of geology there. Emily is a graduate student researcher and laboratory person. Yeah. Okay. This is ThinkTech Talks. You're on the SOEST Hour, and we're talking about down into the center of the Earth and Mars. We'll be right back.
I'm Hong Jiang, host for Asia in Review on Tuesdays.
And I'm David Day, host for Asian Review on Thursdays. Both of us broadcast our respective shows at 4 p.m.
And my topics tend to deal with questions related to environment, culture, history, and sometimes human rights.
And my shows tend to be on international business, foreign policy, geopolitics, and national security. And you can watch our shows live on the ThinkTech website at thinktechhawaii.com.
And you can also watch us on YouTube or Olalo.
So come join us on Thursdays at 4 p.m. I'm David Day.
And on Tuesdays at 4 p.m., I'm Hong Jiang.
Aloha.
Hello.
Okay, we're back, we're live, we're broadcasting from Pioneer Plaza at the core of downtown Honolulu to the world with Julia Hammer, professor of geology at UH Manoa SOEST, and Emily First, a graduate student there. We're talking about, what are we talking about? Petrological puzzles at SOEST, solving them. So the first thing is, I think everybody should know about volcanology, because you guys are both involved in that. We'll talk about the detailed, projects you're on. But what is volcanology, and why is it important to study it here, and why is it important to study it in general?
Okay. Well, if we could have the first figure that shows a map.
Okay, we have a map. There's the map.
There we go. So that's a map it's showing us the elevation of parts of the Earth and also of the seafloor. So you can see in the blue parts where it's water, there's a color coding indicating elevation. So you can sort of get a sense that there's a huge amount of topography just on the seafloor. And you can also see a bunch of red triangles, or maybe they're circles, I can't recall, and they're circumscribing the whole Pacific Basin. And we all know that as the Pacific Ring of Fire, and it's called that because those are locations of volcanoes, each of those dots. And so literally the Pacific Basin is surrounded by volcanoes, and there's an arrow pointing to Kilauea, which is more or less our location now. So we're sitting on top of volcanoes. So step one in understanding volcanology is trying to describe this distribution of volcanoes on the Earth's surface. They're not a random scattering. They don't occur just near the equator. They are present at the South Pole in Antarctica as well. A lot of people think you can't have a volcano in a cold place, but you can. It's not prohibited by any climatic factors. In fact, it's defined by the locations of plates and in the case of Hawaii, the locations of an anomalously warm region in the Earth's mantle that's creating a vent for magma, and the plate is moving over that source of heat, kind of like a piece of paper moving over a candle. And as that happens, the burn marks coming up through the plate are the islands that are the thick pile of lava that's
So if you know where the plates are, you will be able to figure out where the volcanoes are.
Right, and in fact, yeah, you could use the plates to help I mean, you can use the location of volcanoes to outline where the plates are as well. You can go backwards.
Yes.
And they also more or less coincide with the locations of earthquakes on the Earth. So we get earthquakes and volcanoes in similar locations because they're at plate boundaries for the most part, where plates are sliding against each other. And maybe sometimes one's moving underneath another one, and that friction creates not only the seismic signal, but also allows material to melt in the mantle and come up and make a volcano.
Okay, so from the plates and the existing volcanoes, you can figure out where there's going to be an earthquake?
Well, they're interrelated concepts.
Right.
I guess what I'm saying is that even if you didn't have some fancy way of imaging down into the interior of the Earth, you could just scan the surface and find the volcanoes, and that would tell you where the plate boundaries are. So it's a kind of topographic expression of something that's either below the ocean or below
Okay.
the crust.
And it's not at random, as you said.
And it's not random.
And you have a ring of fire around the
Right.
Pacific Ocean.
Right.
What does that tell us, that we have a ring of fire? I mean, how did it get to be a ring of fire around the Pacific? Why is it like that?
Those are, in all cases around the edges of the Pacific, those are places where one plate is diving underneath another one. And when it goes down, it takes sediments and hydrated crust that's been sitting around under the ocean with it. And when that hydrated material moves down, it starts to warm up. And the extra water that's been added is released. Kind of like boils off.
It boils off. The hydrated crust material boils off when it goes down into the hotter part.
Right.
Can we get levels on this? On the top is the mantle. Is that the top?
On top of the mantle is a crust.
The crust.
Yeah, and then there's the
That's
mantle.
you can plant your garden in the crust.
Exactly.
Okay.
A few kilometers.
Yeah.
Okay. How much is it?
A few kilometers.
50
Varies a
kilometers
lot.
down.
It
That's
can
a
be-
lot.
It can be from just a few kilometers up to tens of kilometers.
Okay.
Yeah.
But
different-
theoretically, if you when I was a kid, we were going to dig to China, but
Yes.
I would have found out other things if I had actually done that. So if I dig through the crust, I'm going to find the mantle.
Yes.
What's the how do I know? How do I know I have arrived at the mantle?
It has a different chemical composition. See, so there's that chemistry coming in.
Yeah.
The mantle is much richer in elements like iron and magnesium compared to silicon. Silicon is enriched in the crust. So there's a definite boundary between the crust and the mantle that's based on composition.
Okay, so now I'm in the mantle.
Okay, so you're in the mantle, and
Is it hot?
It's very hot, and it's hot enough to melt, but it's not molten everywhere. So most of the mantle is solid, but at certain spots, either because they're anomalously warm or because of that water that came down with the subducting plate, that's where you get melting of the mantle. And when the mantle starts to melt, that liquid is more buoyant than the solid around it, so it starts to move up. And when it gets to the crust, it can start to melt the crust.
So it's like a living, breathing thing. The crust is going down
Yes.
and melting, and the mantle is coming up. So it's moving.
Yes. Well, in fact, I put a layer of complexity on there, is that the crust is actually just a small piece of what's going down. Part of the mantle is rigid and it's going down as well. But to a first order,
In plates.
yeah, the
Because
plate,
the plate
is a
itself
thick
is
thing.
a thick thing, goes from the crust to the mantle,
Yes.
and it's
And it,
because it's
everywhere
thick.
where the mantle is rigid, but that's part of the plate, so that's going down. And then so the point is that you get this ring of fire in all those places where that melting is going on. But in between, there's not a lot of melt in the mantle. That's surprising to many people, is that
Okay.
in the textbooks they show the mantle as a red donut shape, to make it makes you think that it's this liquid ocean, but in fact the Earth is the mantle is nearly fully solid.
Okay, so now we're in the mantle.
Yeah.
Does the mantle go to China? Or, I mean, what happens if I...
Depends on where you're drilling through there.
There's also a core under the mantle.
Okay, let's talk about the core.
Okay.
How deep do I have to go to hit the core, and how do I know when I hit it?
You know that you've hit it because the chemistry changes again. So there's no more silicate in the core. It's a metal, and the outer core is a liquid. So everything I said about the mantle being mostly solid everywhere, the outer core is mostly liquid, and it's some combination of iron and nickel and sulfur. And then there's also an inner core that's solid again. So that's where our magnetic dynamo is generated, because we have a core that's spinning.
What is the magnetic dynamo?
It's what creates the magnetic field of the Earth.
Oh,
Yeah, a spinning magnet in a magnetic field generates, well, how does it work? You have a magnetic dynamo because if you have a metallic core that's spinning.
it's fabulous,
Yeah.
this stuff. So if I get to the center of the Earth, there was a fictional hero who did this. If I get to the center of the Earth, what's there? Does it say like North Pole or something? You know, like little sign, center of the Earth.
I doubt it, yeah. It would be hard to keep digging since it is a liquid. You would
Yeah.
be digging into that liquid.
It would be, would it be the hottest place? Would it be the heaviest place? Would it have the greatest magnetism? You know,
Yeah, just picture liquid iron metal. So it would be like a steel foundry down there, hot and much denser than what's above it.
would it be red and glowing?
If you could transport a parcel of it instantly to the surface, it would most certainly be incandescent.
Like a steel factory.
Yeah.
Which brings me to a question I asked you before, and I didn't get the answer I hoped for, but I'll ask you my question again. So if we run out of iron ore in the crust,
We
could
will
we
not.
find support? We'll never run out.
There's iron is one of the most abundant elements in the crust as well as in the mantle.
So there's
And
no
Earth,
need.
there's no shortage of iron.
Is there anything down there that would be useful for the development of society that we don't have on the crust?
That's a good question.
Probably the more relevant question is, could we ever get to it?
That's
Yeah,
true. It's
to
not
make it
easy to get
economic.
there.
No.
Yeah.
Yeah.
Right.
Why are there issues about getting to it? I mean, we don't have equipment that will just dig straight down into hot magna and whatnot.
Yeah. I mean, it's thousands of kilometers.
Yeah.
To get.
It's
yeah.
very, very far.
Okay, so the last part of my multi-part question was, why do we care what's down there?
Well, we're on a planet that's dynamic. It is not staying constant through time. It's always changing, and it'd be interesting to know where it's heading. What's next? And volcanoes are one way where heat is delivered to the Earth's surface, and so that's changing. It plays a role in all the cycles
So,
that we depend on the Earth. It's without plate tectonics, without volcanism, it would be a very, very different planet. So the questions of why do we care really kind of comes down to, on many levels, do we care about economically valuable minerals that are forming due to the hydrothermal systems around volcanoes? Because that heat is supplying energy for water to cycle, and that's depositing ore minerals. So there's an economic reason that we care. There's a hazards reason why we care about volcanoes, because obviously people are affected, societies are affected by big eruptions and even small eruptions, and even by quiescent outgassing from volcanoes. It changes the chemistry of the atmosphere.
and
important
we
ways.
need to be able to predict these things or avoid them. And geology and volcanism,
Volcanology.
volcanology. Volcanism is probably religion, isn't it? Volcanology. Worship hot magma. So volcanology will tell us, warn us, and so forth. It's an indicator. I don't want to say canary in the coal mine, but it's some sort of indicator of how things are going. Am I right?
Geologically, with respect to the Earth. Yeah, I suppose you could think of it that way, although the human time scale is so short compared to the geologic one that when it comes to that interface with respect to volcanoes, it's normally a hazards perspective. How can we live in the vicinity of volcanoes, which do produce fertile soils and things that we depend on without risking life and property. So we're in a kind of balance, a harmony with volcanoes that is difficult to manage.
So geologists have a long view of things. You look backward a long way, and you also look forward a long way. It's like your research products should be in time capsules that are buried at the World's Fairground or something, so that everyone can look at them later.
Yeah, well, actually, when you study volcanology, you are working on a geologic process that occurs on a human timescale. So the experiments that Emily runs in the laboratory are not extrapolations to nature. They are operating, at the rate at which a magma can come to the surface or cool on the surface. So we don't. Some geologists are truly working on the million-year time frame, but we're kind of, as volcanologists, we're working at a much more human time scale.
Oh, great. So this is a great time for us to take another break and then come back and talk about Emily's project and the project you guys are working on together. I think we have enough of a basic background now to appreciate it. Okay, that's Julia Hammer. She's professor of geology and volcanology too, I suppose, at UH SOEST, and Emily First, a graduate student and a researcher. And this is ThinkTech Talks. We're at the SOEST hour, and we're talking about getting down into the mysteries, unlocking the mysteries of the deep here and on Mars. All right. Okay, be right back. Castle and Cook, Hawaii. Investing in Hawaii, creating communities, and providing for the needs of our state. Collateral Analytics, empowering the real estate industry to make better informed property investment decisions. The Foreign Trade Zone, bringing the benefits of the Foreign Trade Zone programs to Hawaii businesses and entrepreneurs. Galen Ho, a senior executive of BAE Systems, a global defense, security, and aerospace company. Hawaiian Electric Company, and its affiliates Maui Electric and Hawaii Electric Light Company on Hawaii Island. The Hawaii Energy Policy Forum, incorporating diverse perspectives to design a flexible and forward-looking energy strategy. Hawaii Energy, the state's energy and efficiency program created to help Hawaii's residents and businesses adopt a clean energy lifestyle. Hawaii Gas, helping Hawaii achieve its transition to clean energy and a better energy future. Hawaii Pacific Health, bringing technology and teamwork together to transform healthcare in Hawaii. The High Tech Development Corporation, attached to DBED, is the state's leading technology agency. The Scheidler Family Foundation, supporting educational, cultural, and charitable organizations, including ThinkTech. Okay, we're back, we're live, we're ThinkTech Talks on the SOEST Hour, the School of Ocean and Earth Science and Technology at UH Manoa, with Julia Hammer, professor of geology there, and Emily First, a graduate student there. And now we're going to talk about the two projects that are going on, that these guys are working on. One is, I'm just reading here, and you can explain this in English later, a combined petrologic and rock magnetism study of synthetic Martian basalts, from Mars even, Martian basalts from Mars, and investigating Hawaiian magma chambers using crystals in lava. Crystals just like that, crystals. Okay, so Julia, tell us about the projects. You're the principal investigator. What do these involve?
Okay, so the Mars project is kind of one of the longest lasting projects that I've been involved with, and it started before I even came to UH, when I got interested in some of the results that were coming from the Mars Global Surveyor spacecraft data, indicating that the planet has a series of very intensely magnetized portions of the crust. And if we can go to the for that one, this is a picture of Mars looking at two sides of it, and the colors are again altitude. So the blue colors are lower elevation, and the red colors, warmer colors, are higher elevation. And you can see that there's two kinds of material on crust. There's the smooth lowlands in the north, and then ancient, heavily cratered highlands, mainly in the south. And the magnetic anomalies were detected only in the ancient part of the crust, the ancient southern highlands. And right, and okay, actually, you can go to the next image. Yeah, so those are the vertical-looking stripes are the spacecraft overflight paths, and the blue and red colors indicate the magnetization of the crust. So they're detecting from 100 kilometers above the surface of the planet magnetizations of the crust that exceed any of the magnetizations of Earth's crust. And yet, Mars doesn't have an active dynamo. It doesn't have a core that's liquid and cycling around like we do.
Do we have an explanation for that?
Well, that's the question. special kind of magnetic carrier, a mineral on the surface of the planet or in the crust of the planet that's capable of retaining an intense magnetization over billions of years, because it hasn't had a dynamo active for several billion years. So there are very few minerals that can do that. Hematite, magnetite, pyrrhotite are three candidates, but they have to have very special properties. So in the case of magnetite, which is the carrier responsible for the Earth's magnetic anomalies on the seafloor, which were involved in helping us define plate tectonics in the first place, that magnetite, it can be a strong carrier only when it's very, very small in its domain size. So the magnetic domains have to be nanometer scale, super tiny. So once they get bigger, they lose that ability to retain a strong, stable magnetization.
Could it be something that's not on the periodic table? Could it be
a mineral that we've never heard of?
mineral that we never heard of before? I mean, why are all the minerals in the universe limited to ones we know about?
But they're not. There are new minerals that are discovered on other planetary bodies.
Already?
All the time. Well, we like to work on constraining problems rather than dreaming. Like trying to find something that's
I'm
within our
trained as a
vocabulary.
lawyer, so I like to expand problems.
Well,
Joke.
part B of this is that we do have samples from Mars, even though there's never been a sample return mission to the planet, and those are in the form of the meteorites. So we have these specimens that were clearly sourced from the planet Mars because the gases that are included in the meteorites match exactly the atmospheric composition detected by the Viking spacecraft on the surface of Mars. And there are also other characteristics that make them unique in the solar system. So we had these little samples of the planet. So that gives us a vocabulary of minerals, and they are similar to the minerals that we have in our basalts, but not the same. They're very similar. So to me, it became an interesting question of crystal growth. How can we generate many, many, many tiny magnetite crystals from a basalt whose character that we know something about from the meteorite collection? And so that's what started my collaborative study with a rock magnetist, Stephanie Brockfeld, who's at Montclair State University in New Jersey. So we have this kind of across the
collaboration
continent
with New Jersey. That's cool.
So we cook up samples in the lab, and that's what Emily's going to describe. And we kind of cut it in half and send part of it off for magnetic characterization. And we can discover some really interesting things about what it takes to make something that could be responsible for those anomalies. And along the way, we're also learning about lava flows and how they are erupted on the surface. That's kind of the chunk that is Emily's master's.
And magnetism itself. Am I right?
Yeah.
So, I mean, for example, you could discover chemistry or geology that would create a more powerful magnet than we know yet today. Is this possible?
Like what conditions could we, could we find to tune it? It is very much a Goldilocks problem, because if you...
What's a Goldilocks problem?
Well, if the porridge is too hot, it's not good. If it's too cold, it's not good. But if it's just right, well, it's kind of like that in dictating magnetic properties of a basalt. If you crystallize too much magnetite, then the crystals get really big and they can't retain a strong magnetization. If you cool it in such a way that no magnetite forms, well, then you get no ability to carry a magnetization either. So you have to do it just right, the right cooling rate and the right concentration of oxygen in its environment.
But then you make notes.
And you make careful
So
notes.
you can redo that later.
Yes, you have to reproduce it.
Okay, you have the floor, Emily. Tell us what you do and why it relates to that and how it advances the science. Well,
Oh boy. So my project stems from everything Julie was just talking about. I'm focusing more on the petrology part, like the texture of the minerals in the rocks and what that tells us about the cooling rate. My whole study is based on one of these meteorites that came from Mars, which is called Yamato 980459, named for where it was found in Antarctica. And this particular meteorite, we can look at a picture of it here. This is a backscattered electron image, so you can think of it as basically the darker areas are richer in comparatively lighter elements, and the lighter areas have more things like iron and heavier elements. So that really big round thing kind of in the middle is a crystal of olivine, which, as you know, is also common on the Earth. And there's also other minerals in there of different sizes. But notice how that olivine crystal, if we go to the next one, we can see another one. that crystal is really well formed, has a nice shape to it, and that rim, and you see some other crystals around it. But then if we zoom in even farther, we see that there are lots of even smaller crystals, and we can call these dendrites, if you will, of both pyroxene and olivine, these two main minerals, iron magnesium silicates, that are in this rock. And the different morphologies of all these different minerals can tell us about the cooling history of the rock. And the natural meteorite has been studied by a lot of different groups since it was found, and people have postulated that it was from a lava flow on Mars. But we had some questions about what exactly was the cooling rate of it. Some people thought that based on the morphology of these really small dendritic crystals, it could have been a really, really fast cooling rate, upwards of 1,000 degrees Celsius per hour. And we thought that seemed a little fast, maybe. So part of my work was to do experiments based on this rock to see what happens when you cool it that fast, and could you get these textures if you cool it more slowly. And the cooling rate broadly can tell you something about, well, if it's reasonable that it is a lava flow, which yes, we think it is. And then also, people have postulated before maybe it was a very thin flow because it cooled fast, and sort of these types of constraints. And we're kind of showing that maybe it didn't have to be super thin, and maybe it was more like just kind of a typical Earth lava flow. So what we do, it gets into kind of what we do every day in the lab. If you want to go to the next one. Right, this is kind of how we make rocks. So our goal is to create a synthetic rock that's really similar to that natural meteorite, because we can control the conditions, the temperatures, the gas atmosphere.
You make rock?
Yeah,
Yes.
That's what
I
I'm
know
going to show
that.
you.
Wow.
Yeah.
Modern science.
Since we can control the conditions, then we can look at how our rock is similar or dissimilar from the natural rock and draw conclusions about how the natural rock might have formed. So basically, to make our rocks, we take, in this case, synthetic reagents like oxides, hydroxides, like FeO, CaO, and we weigh them out very carefully in the proportions that match the bulk composition of this meteorite we're looking at. And I've shown that there with a little scale, and we literally grind it up in a mortar and pestle for hours so that it's a very homogeneous composition. And then
Fine powder.
yeah, very
Fine
fine
powder.
powder. And we even put it in a sort of lowish temperature oven to burn off the carbon and things that we don't need. And then that's our starting mixture. And then basically we need to put it on a holder so we can put it in our furnace. And we run into problems with that because we like to use platinum for our holder because it has a really high melting temperature, which we need, and it tends to be pretty inert. But if we go to the next slide, it turns out that platinum likes to take in iron. And our compositions, especially these from Mars, are very iron rich. So when we put our rocks on their little holder wires, the wire tends to suck out all the iron, and then we have the wrong composition. So we have to go through this whole procedure of coating these platinum wires with iron and then annealing it at high temperature so it becomes a true solid solution of iron and platinum that's in equilibrium with the rock we're creating, so that our container doesn't screw up the composition of our rock.
It's kind of like filling up the sponge so that it can't absorb any more.
I don't do that myself, but
Well,
listen, but you need to get back to the same proportions that you started out
Right.
with.
We don't want to mess with our carefully weighed, carefully constructed composition. Yeah, so
Very
as you
tedious.
see in this image, we work with these wires that are, less than a centimeter long, and they have this loop, and go through this whole procedure where I electroplate them using a very high purity iron piece of foil and this solution of iron sulfate material, and you electroplate it, and then you get all the iron coating, and then we have to put these wires into our furnace at very, very reducing conditions so that the iron and platinum will truly alloy.
Yeah.
So that's just to make the holder. And then once we finally have that on the next image, then we can actually do our experiment, which is the exciting part. So we take that powder that we carefully made and put it on the wires. And in that first image, you can see they're hanging on what we like to call our chandelier. So we can hold several samples at a time. So we get sort of replicates of our experiment to make sure that what we're seeing is not an anomaly. And what it's hanging on next to it is a sensor that detects the temperature and basically the atmosphere, whether it's reducing or oxidizing in the furnace. And we run on a reducing atmosphere because that's what they've determined the natural meteorite was formed under. And then we actually put it in our furnace, which is shown in the second image. The actual furnace is on the right. It's that white box, and it's basically a long tube that's heated very, very hot. For example, the melting point of my rock here is about 1450 degrees Celsius. So super
It's just
hot.
dangerous work.
I wouldn't say it's dangerous. I mean, we take a lot of, the furnace is very well contained. You know, we wear all our safety gear and have heat shields. There's not actually, we have water jackets on the furnace, so there's not a part of it when you're putting it in, when you're putting the experiment in the furnace, you're not actually touching things that are hot, and then you don't take it out until, you know, it's done and quenched. And so as long as you're careful, it's okay. But it looks really cool, and you do have to be careful.
We only have a minute more.
Okay.
And we have to move on to the next
Okay.
project.
Well, so you can see what it looks like looking up into the furnace in the hot gas. And then what you get from it, if you skip to the 2 images from now, basically we get rocks and we're looking at how they look like the natural meteorite. And this is a good image because you can see on the right-hand one, we have those really tiny little dendrites coming from our crystal, kind of like the natural rock. And these formed way below 1,000 degrees Celsius per hour. So we know that you didn't have to cool that quickly to get this meteorite that you got from Mars. And the one on the left is also an olivine crystal, but it doesn't look nice and filled in like the ones in the natural rock. So by the same token, we know that there was another stage of cooling that had to be really slow for the natural rock to become more infilled with those crystals. So basically we needed 2 stages of cooling. One had to be very, very slow, probably in the mantle and then coming up from the mantle of Mars. And then the second one is consistent with the lava flow on Mars, but it didn't have to be as fast as people have predicted before.
So you parallel the creation of the rock
Yeah,
in order to
to some
determine the cooling characteristics of the process of the original
Right.
rock.
Yeah.
Exactly.
So, okay,
Exactly.
that's really
That's right,
interesting.
yeah.
Okay, I didn't hear yet about the field trips, but we can get to that later.
Well, field trips to Mars aren't really in the cards, but
Okay, so now the second project, so we can get a handle on that.
Right.
This one's called Investigating Hawaiian Magma Chambers. You should tell them what that is, using crystals in lava. Okay, and this is yours.
well, I'll start out by mentioning that it's I'm one of a team working on this that includes an undergraduate, well, then undergraduate, now graduate student, Samantha Jacob, and also another member of the lab, Benoit Velch, who's here from France working with us. So it's a group effort. But if you can actually go to the next slide, it's to introduce, this picture shows the life cycle, as we say, for a typical ocean island volcano, like the Hawaiian chain volcanoes. And basically, by looking at Maui, East Maui volcano, Haleakala, we're looking at a volcano that's in row 2, column 2. So it's a volcano that's in its post-shield stage. It's already produced the vast majority of lava that it's ever going to make in its lifetime. It's producing small quantities of lava now, but and they have a distinct chemical character relative to what came before them. So the magma chamber that we're studying is basically, we're trying to understand the plumbing system that is still feeding that volcano and has been feeding it for the last, say, 200,000 years or more, when it was in its post-shield stage. So chamber is a shorthand term for really an entire system of magma transport from the mantle
Down deep.
all the way to the surface.
It's not like a lava tube.
No, tubes form in flows on the surface of the edifice, but
Okay.
we're talking about kind of whatever structures there are, be they shaped like cigars, or if they're sills, or whatever kind of bodies and conduits that exist. And so one of the main questions that we try to answer is, how deep is the magma reservoir where it's being stored? Because we know that during a single eruption, you can make a volume of magma that's sizable. So there had to have been a place where it was contained in the edifice, or in the mantle, or in the oceanic crust.
Does this
Where
help
is
you?
it?
Does this help you understand how, for example, the Big Island has created new land mass? That the magma comes up and it goes down into the ocean. All of a sudden, the Big Island is just a little bigger. That's why they call it the Big Island, because it gets bigger.
Yes, now it's the Big Island, but it hasn't always been the Big Island. So earlier I was talking about how there's an anomalously warm mantle plume, and the plate is moving over it. Well, right now the heart of that melting and the plume is under Big Island, and so you can imagine like a ring of intense magnetism right around that plume. But as you get further away, there's less and less of it. So Haleakala volcano is on the outer fringes of that melting. So it's still alive, but it's a much slower, lower flux of magma. So anyway, let's just motivate it by looking at these cool crystals, because in a way that's kind of how it happened. That fellow Benoit that I was telling you about, he is a specialist in identifying.
Maybe our flow manager can zoom in on that.
Well, actually, if
hold
you
it
go
up.
to the next slide, you can even see a better picture of it.
Okay, there's a slide.
Yeah, that's
And that's it. You got it on the camera. That's
right.
great.
That's a detailed picture of what we have here in the studio. These are crystals of clinopyroxene, and clinopyroxene is a really special mineral because it's got a lot of chemical variation accessible to it. And so this is part of my interest in chemistry coming through, that if this crystal were growing in an environment of very high pressure, it will tend to try to minimize its volume. It will try to take a chemistry that's as compact as possible. And it turns out that means if there's any sodium around, it will become enriched in sodium if it can. That's the thinking, is that a crystal grown under high pressure, clinopyroxene crystal, will be rich in sodium. So what we've done in this project is to make very, very detailed elemental maps of individual crystals. So if you go to the next one.
We only have a minute left.
Okay.
Sorry.
You skip over that one. That's a geologic map. One more. That's what these crystals look like when we view them under the microscope. Go one more, and then we'll stop here. So these are a set of images that are showing us elemental abundances at the sub-micron scale. They're maps, element maps of crystals like this, showing the distribution of the sodium. And the traditional explanation would be that the sodium-rich portions of the crystal grew at really high pressure, maybe down in the mantle. That's what has been inferred before. And we're actually challenging that notion, because what we're bringing to the problem is a discovery that there might be other reasons why sodium is enhanced. And so they're kinetic reasons, things that are kind of affecting that tendency to minimize its volume. So, yeah, in a nutshell, if you kind of skip to the very last image, we can give our big conclusion. On the left-hand side, you see a cross-sectional view through Haleakala volcano, showing that there's a sea level that's a horizontal line near the top. Everything above that is what's sticking out above the ocean, and then the rest of it, you can see the mass of that volcano is really quite enormous. And then the things that are shown in the center of the volcano, those are all plumbing structures that people have proposed that can accommodate this post-shield magnetism. And our study is kind of bringing the realm of what's likely to be shallower than what some people have said in the past. So it means that the volcano plumbing system is a little bit more lively than what had been proposed.
But when
on the basis of the same crystals. We're looking at the same crystals that other people have looked at, but seeing them differently.
It's dynamic. What I get out of this is that there's geology and there's volcanology. Volcanology is like dynamic geology. It's happening. There are reactions, changes going on, not only at the small level, at the chemical level, but at the larger level. So that if you were inclined to be a geologist, you'd be really interested in being a volcanologist, because it moves. Volcanology rocks.
No pun intended.
Oh yes, that's an oldie but a goodie. Yes, it's true.
And now, finally, we have settled on a title for the show.
Volcanology
Volcanology rocks. Okay, I'm being told we're out of time. Thank you very much, Julia Hammer, professor of geology and a volcanologist, rocking at UH. In SOEST, the School of Ocean Earth Science, and Emily First, graduate student and researcher there, both working on the same, a couple of related projects, may I say, okay, here at the SOEST Hour, and I guess I would come down after all the possibilities we've considered. I would pick the last one. Yeah, yeah, volcanology
You
rocks.
can print
yeah.
that up and we'll put it on our door.
Okay. Thank you, ladies.
Thank you.
Thank you.
Aloha.